Okay, back we go over here, and we will continue running our do file. So now we have another comment. Specify constraints. Okay, what we're saying here is, in order for this to make chemical sense, we need K1 to be a positive number, and we need K2 to be a positive number. Those proportionality constants cannot be negative. We need to have some G in the system. G0 must be bigger than 0. F0 must be bigger than 0. And in fact, B0 that we start with must be 0 or bigger.
Gary, couldn't K1 and K2 be 0?
Actually, they could be, but less than, or sorry, greater than and less than in a computer is almost the same as greater than or and equal. In fact, in MLAB, it is in the special case of constraints.
So in constraint, whether I write greater or equal or I write greater does not matter.
Does not matter because of the round-off nature of floating point numbers. You can't do something as close, be very, very close to 0 in a computer. You can only be a certain amount close, and then you will drop to be 0.
Okay.
Okay, so continuing, we have a set of constraints that we've defined. Now we're actually going to fit the model to the data. Try to estimate K1 and K2. So fit the model using estimated weights, whatever they are. I'll say a little bit about that in just a minute. But here is the fit. What we gave MLAB is the command fit to find K1 and K2. So we say parenthesis K1, K2 means that's what is to be computed, so that the function b, notice here's a lowercase b, doesn't matter, is fit to the data matrix D. That's the data points. Make the B curve go through these points as best you can with the weights EWT, which stands for estimated weights of the D data, the data matrix, with weights which are basically numbers that say how reliable each observation is. We want big weights on reliable numbers, and we want small weights on more unreliable numbers. So we say with the weights that we compute, honoring the constraints while you do the curve fitting. And we did some calculations that happen to be very fast. MLAB usually is. And we produced the estimate K1, there it is, K1, is 0.4681 something, with an error of 0.065. That's pretty good, actually. That's 0.06, that's about 20% error at the most. This is a so-called standard deviation estimate. We'll say more about the dependencies later, but dependency is good. These numbers they have to be 0.999 for you to be concerned about them as having dependent parameters. And K2 is estimated to be 1.3716 something, again with a reasonably good standard error, 0.02. It took 4 iterations, whatever that means. And the measure of the quality of fit, the so-called weighted sum of squares, is 31.56 something. The e to the plus 1 means 10 to the 1. This is not the mathematical e, this is exponent e. We've got some other parameters we're not going to say much about right now. The constraints did not have to be invoked. We're not up against any constraint.
So the constraints were never triggered?
Well, it turns out probably not. But at least they weren't triggered at the end. When we got these points, these are not up against a constraint.
Okay.
Okay, now we're going to draw a graph of our best fit model. So we're going to call a curve D1. Remember, we defined a curve D0 before. Now we're going to compute B again. What I didn't tell you, perhaps, is that K1 and K2 have actually been changed to these numbers, so that when we solve the differential equation, we will use the new K1 and K2 for that solution.
So the original K1 and K2s have been destroyed?
Destroyed and replaced with the best estimates.
But the graph that we have in the background still represents the original guess?
Absolutely. That doesn't, there's no magic in MLAB. Nothing changes unless you tell it to. Okay? There it is. There's the original guess still sitting there. Okay? Now, another thing about this curve fitting that we just talked about, in order to do the fit of B to D, we had to solve that differential equation for B over and over and over again. So we probably had dozens of evaluations of the differential equation in order to do this final curve fitting. Just like we're evaluating it once more down here to get our graph. So continuing, we're putting a top title on the graph just to tell us what our final fits were. As you can imagine, I got this top title by typing it in after I'd run this fit, but you could, with a little bit of magic, get these numbers to appear on the screen in an actual script by some string commands, which we're not going to talk about today. And there is our best fit, this green curve. And it looks pretty good, doesn't it?
So just to recap here, what the dots represent is our recordings.
Yeah, our data.
Our data. And the dashed line represents
our initial guess.
Our sort of wild guess.
Yeah, wasn't that wild, was it?
Well, no, it was a pretty good guess.
Yeah.
And then the solid line now represent MLAB's computation of what the fit is going to be.
Yeah, it actually improves this guess to be even much better.
It improved it significantly,
right.
In fact.
It did indeed. So it's a very nice fit. But of course, you've got lots of interesting questions. Just because you see a nice fit picture, does that mean you really know something about K1 and K2? Well, you can't make, what's the old saying, a silk purse out of a sow's ear. So you cannot really claim that you know something about K1 and K2 unless you have repeated this experiment many times or equivalently have been able to claim that you have very accurate data. This data is certainly not accurate enough to be able to write a paper saying we know K1 and K2.
Of course. What is interesting here, I think, is that you can see how sporadic the data is. And the art of actually finding the ideal curve to that is really important.
Yeah, it is very nice to be able to do that, that's for sure.